Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at American Academy of Environmental Engineers and Scientists. First off, we want to thank one of our patrons, Black & Beach, for sponsoring this webinar. Here with us today, we have Dr. Bernard and Dr. Downing, both from Black & Beach. Dr. Bernard is Global Practice and Technology Leader, and Dr. Downing is Principal Process and Innovation Leader. Today, they will be discussing the application of S2EBPR to enhance phosphorus removal and recovery. Before we get started, I just want to mention that you'll be able to message your questions at the end of the presentation. Once the presentation's over, and you'll be able to type your question into the attendee chat panel on the left-hand side of your screen. We'll also share their email addresses so you can email them directly with any additional questions you might have. Okay, let's get started. Good afternoon, Dr. Downing and Dr. Bernard. Thank you for joining us today, and we're ready when you are.
Thank you. I will start off with the first half of the introduction to the process, and that will be followed by Dr. Leon Downing. And so next slide, please, Leon. The overview, we're going to talk about conventional, that should be EBPR, development of sidestream EBPR, some case studies about the WRF study, and then about phosphorus recovery. Next slide, please. So we'll start off with some history and case studies. Next slide. The first observation of biological phosphorus removal in the denitrification was in this pilot plant in Pretoria in 1972. And because I tried to fit in 4 stages into this existing basin, I had to have what I thought was a dead space in here, but there was a partition between that and the second anoxic zone. And there were 2 1-inch holes there, 25 millimeter diameter. And I didn't realize that there was an exchange, as you can see from this diagram. But what I noticed was total phosphorus removal down to very low values. They didn't measure below 0.2, and it stayed there for weeks and months. And what I noticed on the profile coming in at about 10 milligram per liter, there was this release in the second anoxic zone to 32 milligram per liter. I didn't know where that came from, but I knew that I had anaerobic conditions. So I suggested the photodox process that I'll show next on the next slide, but with the anaerobic zone up front. So here we ended up with a process where the anaerobic zone is up front, and hopefully the requirement that I specified at the time is that we have an anaerobic zone with no oxygen or no nitrates coming in. And the idea was that nitrates will be reduced in the process to a low level so that there would not be a lot of nitrates in the Razz. This was followed by others like the UCT or Johannesburg processes, all developed to remove nitrates, reduce the nitrate load to the anaerobic zone. But by the time, we had about 10 plants already in operation, but by the time I came to design the plant in British Columbia, it was the Kelowna plant was actually the first one. And by that time, Fusen Chen published their paper that said that the PAOs need a supply of volatile fatty acids. And I realized that there wasn't going to be a lot in the influent. And by the time we got to the west side, Kelowna, which is now called West Side, it was then called West Bank, I decided to add a fermenter where we fermented primary sludge to feed that into the anaerobic zone because there was so little in the influent. Next slide, please. Here is an example of the first such fermenter that was at Kelowna, British Columbia. West Side is just on the other side of the lake. You can actually see the lake there. And the idea was to take the primary sludge and ferment it and produce VFA. And if we're going to do that, then we don't need to pass all the flow from the primary effluent into the anaerobic zone, so we bypassed it to the anoxic zone. Next slide, please. That was perfected in this design for the West Bank plant. As I say, it's now called West Side Kelowna. And the idea was then to have the primary sludge fermenter here and then bypass most of the primary effluent to the anoxic zone. And the plant worked very well, but next slide, please. Over the period, they reduced the flow to the primary effluent to the anaerobic zone, and the plant just performed even better. Next slide, please. And here you see a typical profile at that time. And what was surprising was this uptake of phosphorus in the anoxic zone, which meant that these PAOs would also be able to take up phosphorus under anoxic conditions. And then in the aerobic zone, it was reduced to very little. It's plants running mostly at less than 0.05 ortho-P in the effluent. Next slide. What we discovered later is organisms, PAOs like Tetrasphera, they can denitrify and uptake phosphorus under anoxic conditions. I just spoke to Jerry Stevens, and he said that basically all the PAOs are Tetrasphera in this plant. Next slide, please. So that led us to refocus on sidestream fermentation, which was, I have to admit that it took me a number of years to realize what really happened in the pilot plant, that I was having sidestream fermentation. But developing sidestream fermentation is developed into mainly these four flow diagrams. Number one flow diagram is where you have a normal anaerobic zone, conventional plant, but it's not performing. And what you see is if you switch off a mixer in the anaerobic zone, you can get fermentation at the bottom of the tank. In the second one down below, we do the same thing, but we do it outside the basin. We have the anaerobic zone and then pump some of the mixed liquor into a fermenter and feed it back into the plant. The third one on the right-hand side is first proposed by Lamb, and that means taking some of the Razz and ferment it and feed it in, and notice there's no anaerobic zone. And then the last one is the same as the one above it, but you add some form of carbon to the process. And I'll give you examples of these four. Next slide, please. Here is an example of where we had in a conventional plant. It actually worked quite well. We had enough VFA in the influent. And then one day it stopped removing phosphorus, and we discovered that they were adding nitrates to the collection system to combat odors, but it also destroyed the VFA. And so what we did is we had three anaerobic zones here. This is a retrofit of an existing plant. Some aeration was added, and then anoxic and anaerobic zones. And by switching off a mixer in one of the anaerobic zones, you can see down below here on the graph, that blue line is the orthophosphorus coming out of the secondary clarifiers. It's down to the 0.1 level. Next slide, please. The next one was the next one where we take it outside, and here what you see is this L-shaped anaerobic zone. This is a plant in Lawrence, Kansas, called Wakarusa. That's the anaerobic zone, and then next to it you see the sidestream fermenter, where 10% of this mixed liquor was pumped in to here and then fed back into the anaerobic zone. The plant consisted of the anaerobic zone, the sidestream fermenter, the anoxic zone just above it, and then a carousel system for nitrification and denitrification. Mostly the orthophosphorus was running at less than 0.04 milligram per liter. Next slide, please. Here's an example of the LAM approach, where you have the 4-stage nitrification denitrification process with sidestream fermentation, taking a bit of the anaerobic zone sludge and ferment it and put it back in. And this plant was built in South Cary in North Carolina, and is still working fairly well today. Next slide, please. Same concept, the same concept was used in Denmark, and they have developed this where they have probably about 50 plants in Denmark that is doing the sidestream fermentation. And they claim that they don't get GAOs when they put this anaerobic sidestream in there. Again, notice that there's no formal anaerobic zone in the process. Next slide. It's the same concept. Next slide, please. And it's the same concept here, sidestream Razz fermentation, but this time adding some gravity thickener overflow. This was a Denver Metro, 100 MGD plant. And by using this existing basin, it was not necessary to build anything new to get biological phosphorus removal in this normal MLE type plant. Next slide. It shows what happened when this was done. You can see the orthophosphorus down below here going down to very low levels. Next slide, please. I just want to come back to this plant in Wakarusa because for some reason, and we're still working on it, we are getting granular sludge. And you can see the sludge on the left-hand side. And on the right-hand side, you see a picture there. And that is in the carousel ditch. And what you see is a clear layer of liquid on top. And down below, you see the revolving, shall I say, masses of granules that we get. We are still looking into that, but there's some exciting concepts that we can develop from this. Next slide, please. And I wanted to show you this as a 32 MGD plant in North Carolina, where we did the same thing that we did at Denver, and that is we took 2 of the aeration basins out of a virtual 13 aeration basins and reversed the flow through there and have this as a sidestream fermenter, take about 10% of the Razz in there and the gravity thickener overflow, and then feed it back into the inlet to the plant. And that reduced the orthophosphorus over an 8-month period to 0.23 milligram per liter. But what was very interesting about this plant, I must just add that it was designed as an AO process, but with nitrification. So the nitrate in the effluent is about 20-25 milligram per liter. And that nitrate going back into this A zone, it's basically an anoxic zone. It's not an anaerobic zone. But because of the low SBIs we're getting, the SBI of those plants running around about 50 milliliters per gram, it was possible to take out these aeration zones and not derate the plant at all. We can still run it because we get a very good SBIs. Next slide, please. That ends my introduction, and I'm now handing over to Dr. Leon Downing.
Thanks, Dr. Barnard. So I'll try to pull this into more like the design and application side of things, and build on some more recent Water Research Foundation project work that we've been doing. So when we look at kind of the evolution of our understanding of S2EBPR, well, there we go. What we're really focusing on now is our phosphate accumulating organisms, and what we really need to think about is like the BOD storage and anaerobic conditions, and this all builds off of what James has been working on for decades, right? Where we have under anaerobic conditions, some of our BOD, mainly our volatile fatty acids, are used to store this PHA compound. It's just like a carbon storage compound, and while they do that, they're breaking down some poly P bonds that they have internally and releasing phosphorus. So that's why we always see this phosphorus release in our anaerobic conditions. And then in aerobic conditions, they're uptaking oxygen, or as James showed, nitrate. They're breaking down that PHA to restore this poly P, and they suck up a lot of phosphorus. And so a lot of times as engineers and operators, we're focused on the phosphorus part of their cycling, right? We think phosphorus must be a big part of, it's what we're trying to remove. So we call them phosphate accumulating organisms. But the reality is that they're really carbon storage organisms, right? They have this carbon storage mechanism that they rely on that gives them kind of a competitive advantage under anaerobic conditions, where they can access the VFAs, like these BOD sources, and store that carbon for use in the aerobic conditions, or anoxic conditions. And so with the evolution of EBPR, and how we've conceptualized how this happens, initially we said, oh, okay, well, to do BioP, like we need to have volatile fatty acids in the influent, and that's going to drive this. But our our question then, and that James kind of showed, is that, well, why does it have to come from the influent? Like, why can't we find other ways to generate this VFA to drive this PHA storage, and select for these carbon storing organisms? Um, so when we look at these side stream configurations, like what's the advantage, right? Um, so S2EBPR generates carbon from biomass to drive EBPR. So conventional configuration, right? We've got an anaerobic zone up front. It's dependent on our influent VFA. It can be sensitive to wet weather, sensitive to seasonal variability. Something that we're with S2EBPR that is saying anything with EBPR is wrong is just saying, okay, our conventional one, we focus on doing everything in this front zone. Um, with S2EBPR, like James showed, we've moved this anaerobic zone potentially to the side stream. We're diverting a portion of our Razz, and in like the purest form of S2EBPR, which is like Razz fermentation, we're really using the COD that's stored in our biomass to create VFA in the side stream, and essentially store PHA in our cells in the side stream reactor. So when they come around to the influent, we've stored up that PHA, and now they're going to use that PHA to store poly P, and that takes up phosphorus. So you're kind of instead of having this be all in the same flow diagram, it's more like carbon storage here, phosphorus uptake here. And so that's where we're moving to, is they're kind of diversifying the COD fractions that our PAO ecology is accessing. And I think the neat part about this is that it's really kind of developed from like operational experience, right? Plants operating in different ways, and now we're just trying to understand it more on a more fundamental level, so we can develop design guidelines and best practices around it, kind of taking in all of this operational condition. Um, so why is this impactful? Why is moving to the side stream impactful? So one part of it is it gives a lot of flexibility for repurposing of infrastructure. So there's a lot of facilities out there that have unused tankage, but that tankage maybe isn't in the process flow diagram, where you can have all the influent and Razz come into that tank and turn it into an anaerobic zone to kind of get that conventional BioP configuration. But maybe there's some old tanks that are out of the way, right? But if we're really just diverting Razz to those tanks, instead of having to take primary effluent and Razz, and it's just a portion of it, well, it can become much more hydraulically attractive, because we're just pumping a portion of Razz to those tanks and then returning it back to the influent of the aeration basins. Reusing that tankage can save a significant amount of capital, right? And so when we look at one example facility where a conventional BNR was looking at like a $35 million investment, the S2EBPR reduced that more to like 18 to $20 million. And so and it's really just from repurposing of tankage and efficient use of carbon. The other major benefit is that we're seeing in facilities that moving the selective pressure into the side stream reactor, you're diversifying your COD source, and you can see improved stability. So this was some testing that Clean Water Services did a few years back, where they had conventional EBPR, and you kind of see the distribution of effluent phosphorus, where their 90th percentile performance was about 0.8 milligrams per liter, and they got above 1 a portion of the year. In a parallel S2EBPR train where they were doing some Razz fermentation, they significantly flattened that curve, right? So they're able to get more consistent performance because they diversified their carbon source, right? So whereas they might have been carbon limited proportions of the year with a conventional EBPR chain, now that we're accessing some of that COD that's stored in biomass, we're able to improve our stability and essentially get lower effluent limits. Right, so that's the why, the impact, and there's going to be a report, in about 9 months where it's a Water Research Foundation project that's developing practical guidelines based on experience for these Razz fermentation or these fermentative EBPR configurations. So we had 21 participating utilities globally. So some of the Danish facilities are involved in this. A lot of North American facilities. It's a little over $1 million of investment through all the different sources. And our goals for this project are, to develop design criteria for these fermentative processes, identify the operational tools, and then recommend kind of process modeling guidelines. So I'll spend kind of the rest of the presentation talking about these design criteria, where we're kind of going to, and the direction that we're looking at for designing these fermentative EBPR processes. Oh, stuck again. Sorry. All right. So what are the design concepts for S2EBPR? When we're designing for these like a side stream EBPR process, we really have to have an understanding of the whole plant COD balance. All right. So just kind of looking at a very generic sort of process flow diagram, when we're thinking about having a Razz fermenter and how it's going to work, the first thing we have to understand is, well, how much carbon can we actually access from that Razz, right? How much COD is actually going to be available? And that COD availability from our volatile solids, the way we know that there's enough is we have to look at, okay, well, this is our COD source. This is our ability to make PHA. Well, we have to make enough PHA in this Razz fermenter to uptake the phosphorus that's coming into the mainstream reactor. So we can look at the influent phosphorus load. We can look at the different characteristics of the influent, the Razz nitrate, kind of the SRT of the system. And this is a big range, but we'll have the ability to produce 1 to 4 milligrams of COD per gram VSS hour that we add into that Razz fermenter. So now we can get a sense of, well, how much COD do we have available in our Razz? And we can say, is it enough for our influent phosphorus, or do we need other sources? And so if it's enough, you can just do a pure Razz fermentation configuration. But if it's not, if you're projecting a COD shortage, you need to look in other places. So one place we can look is just the RB COD and VFA in our primary effluent or our influent to our aeration basins. You can still have an anaerobic zone at the front of the aeration basins, and kind of have a combination of sort of side stream and mainstream. The other option is to look at a supplemental carbon source. So like James showed some examples with the gravity thickener overflow or primary sludge fermentate, where you actually add in a certain mass of carbon into your Razz fermenter to make up your gap. And so again, it doesn't have to be all the way to primary sludge fermentate. If you add just some form of COD, it can get to VFA inside the Razz fermenter. You can also look at other sources. So we have one facility that's using cranberry juice wastewater, right, and adding that in, and that's their carbon source to make up that gap. And so the question we're trying to develop an answer to for design guidelines is, well, how many pounds of COD do we need for this kind of PHA charging in the side stream, and then how do we get that COD? So that's kind of how we're trying to think of this holistic system with these fermentative EBPR processes included. So these are the same flow diagrams that James showed, but we wanted to reemphasize that with this kind of COD balance in mind. Now, when we think about these from an unmixed inline fermentation where you just turn the mixers off, if you're doing BioP already and it's kind of working, or maybe you have some instability, well, by allowing some fermentation of biomass inside that anaerobic zone, it can maybe give you just a little bit more carbon to help you get over that hump, right? So that you can maybe get a little better performance. If you're looking at kind of a new facility or improving or modifying infrastructure. All right, so these two pure side stream RAS reactors are saying, well, if you have some existing tankage that's maybe offline someplace, or you have excess aeration basin capacity, maybe you can divert your RAS into that tank, capture the COD kind of value that's stored in that RAS in your fermenter, or maybe add in a little bit of volatile fatty acid or other or carbon source to kind of boost it and make up your carbon deficiency. And then the side stream mixed liquor fermentation is just taking that. What you're trying to do is say, well, I've got my primary effluent or influent coming in, I mix it with my RAS in this zone, but maybe you've got like some particulate COD or colloidal COD that can't really drive that PAO metabolism in this anaerobic zone. But if we give it a little more time, we can break some of that. We can ferment some of that influent COD, make it into the COD that our PAOs need, and then send it back into the anaerobic zone. So just a quick experience, and this is a couple of facilities that James mentioned as well. So that Wakarusa is really the SSM. So we outline this where you have the L-shaped kind of influent anaerobic zone. You pump to divert, and then allow that to move through. So the driver, why did they use SSM? Well, they didn't have influent VFA. They had plenty of COD, but it wasn't in the right form. So it just needed a little more time to get into that accessible BOD form for our PAOs. And they've been getting down to the zero 0.2 milligram per liter phosphorus. So a facility that maybe a decade ago we would have looked at the wastewater characteristics and said, nope, you can't do BioP there. Now they're doing BioP, getting a zero 0.2 effluent phosphorus with no chemical addition. SSR plus C, so this is where we have RAS coming into a repurposed aeration tank, and then primary sludge fermentate or GT, gravity thickener overflow, kind of coming into that tank, and then going into the back of the basin. So this is kind of a retrofit facility. The driver for a lot of these RAS fermentation facilities, especially in the U.S., um, is retrofitting, right? So if we have existing infrastructure that we're trying to find a way to repurpose, this mixed liquor, side stream mixed liquor is difficult to maybe repurpose infrastructure for it. It's kind of a unique configuration. Maybe it's possible, but a lot of times it requires some new tankage. This RAS fermentation, it's pretty easy to implement a lot of times with existing infrastructure. And for this facility, they've reduced their chemical use by 75% for phosphorus removal. So it's a huge savings with relatively small investment in infrastructure. There's a pure SSR facility where they had an old clarifier that wasn't in use. Again, you just pump a portion of RAS to that clarifier, let it ferment, return it to the aeration basins. Again, the driver for this is existing infrastructure, and they've gotten an 85% reduction in chemical use for phosphorus removal. So, very different facilities across the board, different drivers, but still trying to rely on these principles of fermentative EBPR to kind of reduce cost and reduce effluent phosphorus discharge. So what are the design challenges with implementation? We wanted to spend a little bit of time on this. We're kind of getting a good sense of the COD balance and how we do the math around that. But what are some of the more design challenges associated with implementing these side stream processes? So one thing is mixing energy. So really, we don't need a lot of energy. You just have to give enough that RAS that you're diverting is kind of turning over. We actually don't mind if it settles a little bit as long as it eventually makes it out of the tank. Because if it settles, it gives you a little bit more sludge retention time, and you get more fermentation. Um, and so this was an example in Wisconsin where they were able to repurpose a tank. They just put in a few submersible pumps, kind of a header on the RAS discharge, and it gives enough mixing where you do TSS profiles and it's essentially mixed. The one challenge, and I'll show this on a couple facilities with repurposing tankage and reversing the flow, is that you can have scum capture, and it's amazing how much scum can come out of RAS. So for this facility, it's an underflow discharge out of the tank, and it just traps that scum. And so if they do a permanent installation, this is really just a demonstration test now. There'd have to be some way to have an overflow so you can get the scum out, because you do get a lot of scum coming out of RAS when you let it sit for a while. So this is just another example of scum accumulation, and it can be pretty thick during cyclic mixer operation. So I mentioned that we maybe want a little bit of blanket to develop in these tanks. There's nothing wrong with some solids settling, but if you're not mixing it really thoroughly all the time, you can get a lot of scum accumulation. So this is a plot from one of the facilities, and we looked at this concentration factor. So it's using online TSS data, kind of manipulating the mixer cycle operation, and then looking at like the TSS concentration of the Razz coming in versus the TSS concentration of the Razz like in the bottom of the tank. And this concentration factor is that ratio. So that concentration factor is 2. It means that the Razz kind of in the bottom of the tank is twice the concentration of what's coming in. And that's a good thing because now we've kind of decoupled the HRT SRT a little bit, and we're giving that biomass a little bit longer to ferment and make a little bit more COD. The challenge is that the scum was pretty intense. So then they went to kind of more of a more aggressive mixing schedule, trying to actually get a 1 or even less because you're breaking down some solids that help with the scum. The ultimate solution though was just to have an overflow weir to control the scum. So let the scum get out of that system. Just be a hydraulic flow was the solution there. So again, the challenge was scum removal, but we can take care of that if we're aware of it. But with our cyclic mixing, we can really get a lot more HRT in our tank to give more time for that fermentation process to happen and kind of generate more COD to drive our PAO metabolism. Um, this facility is also another example of using mixers and trying to optimize them. So we had 5 mixers in a plug flow tank, and so in the middle of the tank, they really ran those mixers on a pretty minimal cycle. And this just looks at the TSS concentration in the top 12 inches of the tank. So at the influent and the effluent, those are the green and blue lines. You kind of have similar TSS concentrations, pretty high. So you kind of have those mixers on all the time to kind of reincorporate what's coming in, and then make sure what's going out is pretty consistent concentration. But in the middle of the tank, they turn those mixers off for the majority of the time, and they actually get a pretty clear layer at the top of that basin. Um, and what that does is it just allows more fermentation. So I think there's a lot of optimization work that can still be done to look at, well, how do we design our mixers and operate our mixers in these fermentative processes, to allow for good fermentation to happen, but also like consistent mixing at the influent and effluent of our tanks. So some of the takeaways from S2EBPR, it's a low carbon, stable biological phosphorus removal. When I say low carbon, it's not that the PAOs necessarily need more carbon at a fundamental level. What I'm saying is that it's allowing us to run these tanks where we're allowing our Razz to ferment, and we're accessing different types of carbon to drive our biological phosphorus removal process. So it's maybe a lower carbon from the influent, because we're accessing some of the carbon that we stored to drive that PHA storage. Um, it really allows us to maximize existing infrastructure, so we can look at different tankage and different availability that maybe isn't, you know, hydraulically, like influent hydraulics doesn't make a lot of sense, but because it's a side stream tank, we can be more creative. And then we have our mixing and configuration details determine the success of our S2EBPR. And so again, how do we get scum out? How do we cycle mixers? That's really one of the big design challenges with these systems, is just making sure that that practical part works really well, and that can enable that good carbon cycling. Okay, so that was, James gave the background. There was a lot of detail on S2UPR. One thing we want to talk about a little bit is just how this ties into resource recovery, because we sometimes focus so much on the details of BioP that we forget that there's actually a much larger driver for doing this. So when we think about phosphorus, like why recover the phosphorus, there's been a lot of discussion of this over the last decade around, well, how much reserve phosphorus do we have globally? How much do we need for growth? Um, there can be debate about that, but one thing that isn't really debated is that phosphorus is really concentrated in a few countries. We're fortunate in the United States that we have a lot of phosphorus reserves in rock in Florida, but it's a small sliver of the global availability. And whenever anything is only in one spot, it just makes it a higher risk. I've heard people try to say this is like a national security issue, right? Like we don't want to run out of phosphorus. I don't know that I would go that far. But it is something we should be aware of, that managing phosphorus and is of global significance. So if that's a driver, we should be thinking of ways to recover that phosphorus. And this is a figure from James that he adapted from this presentation, where it says, okay, well, we've got wastewater coming in. We go to our wastewater treatment plant, and we discharge effluent. So all that 90% of the phosphorus that comes in ends up in our biosolids. If we're doing biological phosphorus removal, we can now try to extract that phosphorus from the biosolids, and in a lot of different ways access it. If we don't extract the phosphorus, like if it's chemically bound, it just stays in our biosolids, and it ends up, either it can get incinerated or disposal. Even for land application, that phosphorus isn't necessarily available. So there's been a lot of work to say, well, how do we recapture this phosphorus now? We spent a lot of energy pushing that phosphorus into our biosolids. How do we now pull that out? Um, and the other aspect of, if we can pull the phosphorus out of our biosolids, it can actually make the biosolids themselves a better fertilizer value. So our typical biosolids are kind of imbalanced from a nitrogen to phosphorus ratio, especially at biological phosphorus removal facilities and chemical phosphorus removal facilities. The plants don't need quite as much phosphorus. So if we can find ways to extract that phosphorus and make it a fertilizer that can be used where it needs to be used, it can actually make the biosolids a more valuable fertilizer, more locally. So if you know this is mainly focused on biological phosphorus removal, but I think we've all probably seen a lot of presentations on nutrient harvesting through struvite recovery, right? So if we look at our liquid stream, we spend a lot of time pushing phosphorus into our biosolids. We then digest those biosolids, so that we can have energy production. But what that ends up with is a lot of that phosphorus back in this liquid stream. So these high recycled phosphate loads from dewatering, you know, from a detrimental standpoint, they can lead to a lot of struvite production. Um, but it also gives us an opportunity to put in nutrient recovery. So again, I'm not going to spend a lot of time on that, on the phosphorus harvesting, but just to kind of put out there that if we can do good biological phosphorus removal, it gives us the ability to harvest some of that phosphorus at a facility where we've done anaerobic digestion, to make a valuable fertilizer product, and kind of close the phosphorus loop, right? Instead of mining it, um, using it in agriculture, having it end up at the wastewater treatment plant, and then discharging it into the water, we can close that loop a little bit and keep reusing that phosphorus in our systems. So there's this has gotten a lot of press, again, the past 5-6 years. A lot of facilities have come online making tons and tons of phosphorus per year in a reusable fertilizer product. There are a lot of drivers to this. It's not just about making a struvite product. It does help limit detrimental struvite. It can make biosolids, um, dewatering more efficient. You can make the biosolids production better, like if you're pulling that phosphorus out. So I just put it up there to say, it's not just uh, not only the environmental sustainability that is interesting from this nutrient harvesting standpoint. It's also some other whole plant impacts that we benefit from doing these type of processes. James had wanted to make sure we talked about this too, because it's something in Europe that's very becoming more common, is incinerator ash. So if we are incinerating our biosolids, that phosphorus is still there, right? Phosphorus doesn't go away. Um, and so I believe these in some facilities in Europe, they're actually kind of having a dedicated deposit of ash from incineration as sort of a future mine for phosphorus. So rather than mixing it and landfilling it, it's like, well, no, let's maybe it's not economically viable right now to pull that phosphorus out of our ash, but it will be someday. Let's kind of sequester and keep that ash in a spot, so that when we have the technology and the drivers, we can access that phosphorus. So that's very long term thinking, but it's pretty interesting to say, well, if you do have that ash, it is a future resource that we can recover. Um, the final thing is urine recovery as the kind of the final frontier. We just wanted to throw it out there to kind of whet your appetite for liquid gold. Urine has most of the nitrogen and phosphorus in our wastewater. Rather than spending all this time trying to treat the phosphorus and nitrogen, um, at the wastewater treatment plant, if we did urine separation and collected that urine, we wouldn't have to put so much effort into biological phosphorus and nitrogen removal, but we could use that as a direct fertilizer. Obviously, that's a big leap, right? If you have the equivalent of a milkman coming around to kind of collect your urine, or parallel collection systems, but it is a pretty interesting concept to think about, and maybe the most sustainable way to deal with these nutrients. So just a quick summary of where we've been, where we are going. So takeaways, biological phosphorus removal, it's an established but evolving process. We're finding more and more new ways to be efficient with it, and kind of move through different process configurations that fit a lot of different facility drivers. If we focus on biological phosphorus removal, it does facilitate nutrient harvesting. And this harvesting of phosphorus is kind of a more economically sustainable approach to nutrient management, right? Kind of closing that phosphorus loop. But it all comes back to if we can find more efficient ways to do biological phosphorus removal in our facilities. So with that, I'll wrap up the presentation portion, and we can start taking some questions. I know we have a couple different ways that folks are typing in questions. We'll try to catch a few of these online.
Thank you so much, guys. We appreciate it. So if you want to type in your question, you can go to the attendee chat in the left-hand side of your screen. And you guys, there's already a couple questions. You guys can get started on answering them. Thank you.
Sure, James, I can read them out, and then one of us can chime in. So there's a
Sure.
Q&A spot and there's a chat spot. So I'll grab those Q&A ones first. Jan asked if we were still having the seminar. I know we were a little late. Apologize for the couple minutes of being tardy, but check that question off. The second question was, can a 1.7 milligram per liter total N and 0.16 milligram per liter total P be achieved? And if so, what technology assures compliance with these limits? So I'll take a first stab at that one. So it's, to us, what we're presenting on today, makes the most use of your carbon and the most efficient way to do biological nutrient removal, right? So if we're capturing some of these sidestream, this Razz, the COD bound in the Razz to drive biological nutrient removal, it makes your carbon go farther, which allows you to get lower effluent limits. Now, that might not be the whole solution to 1.7 and 0.16, those are pretty low limits, but it's part of the package. James, what do you have to say about these very low limits for both nitrogen and phosphorus at a facility?
Yes, that is a real challenge, because I remember somewhere in Florida, a guy said, I can give you low nitrate, I can give you low phosphorus, but I cannot give you both. But I think we are getting closer to that concept, but it'll take a multi-stage process to really do that. I know that at somewhere Reno, Nevada, they have a total nitrogen level of less than 2 milligram per liter, and they take a 3-stage process to do that. And the first stage is a biological phosphorus removal system that is actually so efficient that they have to add some phosphorus again for the later processes, for the nitrification and denitrification. But yes, it is a real challenge, and it's very difficult to do all of that in the same basin, getting down to those low levels. It needs a little more add-on processes.
Thanks, James. So next question we had was, what's a typical HRT for sidestream fermenter? So I'd say the minimum is 12 hours. Maximum, it's somewhere in the 24 to 36 hours. What it really comes down to is, how much carbon you need, what kind of fermentation rate you can get, and that drives that sizing.
Yes, I could just add that is based on, say, 10% of the Razz flow, and the Razz flow may be only half of the main flow. So what we have found is basically it's no bigger than having an anaerobic zone in the conventional process. You can actually reconfigure an anaerobic zone to be a sidestream fermenter also. You want to add anything, Leon?
No, I think that covers it. Let's see. Next question is this technology proprietary? Any chemicals involved in the project? It's not proprietary. I mean, there was some patent on one configuration at one point, but doing a sidestream Razz fermentation tank is not proprietary. As far as chemicals go, I mean, it depends on the facility. I mean, some facilities will do some chemical polishing. Others, may need a lot of extra carbon. I know like Micro C is like a commercially available one that folks have used, but you can also just use like waste carbon products. But yeah, not proprietary. Let's see, a couple extra questions that we have coming in. Oversizing an influent anaerobic zone versus having a side stream process. I think an oversized influent zone. It's kind of like a mixed liquor fermentation reactor. The challenge with having it just be the influent, unless you include step feed, like you're losing kind of the benefits for like wet weather treatment and that stability associated with having a side stream reactor. So, James, any comment on just making a really big influent anaerobic zone?
Yeah, rather than increasing the size of the anaerobic zone, switch off some mixers. That's what we did. That increases the retention of the sludge in the system without having to make the zone much larger. But yes, oversizing the anaerobic zone was mentioned as a possible alternative.
Mhm.
But switching off mixers, you can do it more economically. And when you switch off mixers like that, depending on the design of the process, as Leon said, one has got to pay attention to the scum management. But in many of these plants, we find it not to be a problem. Next one.
Yep, 1 second. Let's see. Can biological excess sludge reduce by using S2EBPR process, especially by fermentation of Razz flow? So I guess the question would, do we reduce like our WAS rate? Like do we have less waste sludge?
I would say what we see is we're still working on it, but it seems to me from all the plants where we have done it that we are getting better SVIs. Better SVIs, it's not less sludge necessarily, but it is, it takes up less volume. But I know some work has been done, especially with this cannibal process, and there were some positives and some negative results, but it would appear from a paper by Gould that you can get these super hoarders, PAOs that really hoards a tremendous amount of phosphorus. And what they have managed to do in some plants is actually reduce the sludge. And what we are doing is not dissimilar to what the cannibal has been doing, but we haven't really studied very well. And it could be that we are reducing the sludge production, but we'll have to do more studies to do that. But as I said, the cannibal process uses similar concept to take the sludge and ferment it and put it back in and then reaerate it again. And they have found that they are reducing the sludge production. But I think the main advantage to us is the lower SVIs that we see. That makes it, you can handle the same sludge in less volume. Next.
Yeah, I think we have time for like 2 more questions. So one, can grit wash and septic tank be used as carbon source to fermenter?
I have heard that proposed, and yes, any source of carbon that you can ferment and pass on. So I think if you can ferment that and then take the liquid from the top and pass it on. It certainly would help. And as Leon explained, any source of carbon is a help because it's really a carbon management. Biological phosphorus removal is more about carbon management. Leon, you want to add something to that?
Nope, that was perfect. So last question. Is would the addition of chemicals such as alum to the secondary clarifier affect the fermentation process in any way? I
Well,
can I can take that one. So I
sure.
think it'll, if you bind up too much of the phosphorus chemically, like there won't be the ability for the PAOs to kind of store poly P, and so it does limit like the effectiveness of establishing that PAO population. But when you turn the chemical off, it does establish over time. So you can have a balance. So at two of the facilities that we showed, like they did add chemical to the system as well. But you got to kind of wean off of it a little bit before the PAOs can establish and then find your balance between the two.
Yes,
So
I
Mike,
could just add that one of the slides I've showed of a plant in North Carolina, we're doing the BioP only on half of them. On the other half of the plant, the chemical addition is added, but they've got this AO process. And in summer, it seems to be working okay, and they reduce the chemicals to near zero in summer. So it is possible, but it's a balance, as Leon said. I remember one plant where we did try to augment the BioP by adding chemicals. We ended up by just adding chemicals, and I know, for instance, the West Bank plant, because they have complied with the 0.25, the operator is very careful and he's set his chemical addition to whenever the ortho-P goes above 0.08, he starts adding chemicals. And at one stage, he added chemicals and he had a hard time reducing that again. So it's as Leon's explained, it seems to tie up the phosphorus, and then the PAOs cannot get added. Okay.
Okay, great. Thank you so much, everyone, for all your questions. And like I said, if you didn't get a chance to type in your question, you can email them directly, and they're happy to answer any additional questions. Our next webinar is scheduled for September 22nd, where we'll sit down with the CEO from Alexandria Renew Enterprises to discuss healthier waterways, healthier Alexandria, and partnering with the community for project success. The page to register for this webinar will open as soon as this session ends, and it will also be on our website. So that wraps up our event for today. Thank you so much, everyone, and have a great day.
Thank you.
Bye-bye.